Dear Professor, ladies and gentlemen, good morning. I'm honored to have the opportunity to speak at this conference. My name is Guobin Zhang, and I come from Shanghai University. Today, my topic is applying probability model to the genetic algorithm-based crowd rendering task scheduling. And in our work, we propose an improved task scheduling algorithm based on genetic algorithm for crowd rendering task scheduling. And there are 5 main aspects to the topic. The first part is the background of our research, and the second part is task scheduling of PMGA in crowd rendering. PMGA means that the genetic algorithm based on probability model, and this is the algorithm we proposed in our work. And the third part is our experiments and analysis, and another part is a summary of our work. At first, we are going to make an introduction about the background and the problems of crowd rendering and the task scheduling algorithm. The model of crowd rendering is similar to cloud computing. The rendering users submit the rendering tasks to the remote server with the help of high-speed internet, and then the tasks are executed at the server. After all tasks are completed, the rendering results will be merged together and returned to the users. And crowd rendering task scheduling is to allocate the tasks to the computer nodes by applying appropriate scheduling strategies, which enables to minimize the time, lower the cost, and keep the load balance of resources. And most cloud computing rendering platforms adopt MapReduce to support distributed computing, and many studies have proved that the problem of task scheduling on the cloud environment is an NP-complete problem. So it is a process of finding a global optimal solutions and strategies for scheduling tasks. And many researchers have proposed many intelligent algorithms for task scheduling on the cloud computing environment, such as particle swarm optimization and simulated annealing algorithm, and anti-cloning algorithm, and genetic algorithm. And they have made some improvements to these algorithms in order to get the optimal solution for task scheduling strategy. However, due to the heterogeneity of the cloud computing environment, we will face some problems, such as easy to track in the local optima, premature, and other defects. And the improvements of some algorithms ignore the guiding law of the information in the process of evolution, and the adaptability are not robust enough. The scheduling time and cost always can't be balanced well. And let us have a look at the genetic algorithm. Genetic algorithms, here we call it GA, and it's commonly used to generate high-quality solutions to optimization and search problems by relying on bio-inspired operators such as mutation, crossover, and selection operations. And the adaptive genetic algorithm, here we call it AGA. It takes a dynamic automatic adjustment for crossover rate and mutation rate, and it improves the convenience speed of genetic algorithm. But in SGA, there are only one population, and the value of crossover rate and the mutation rate are fixed ones. In the adaptive genetic algorithm, It is slightly slow at the beginning of the evaluation process. Beyond that, the fitness function is established only for one target to evaluate the solution domain. In order to improve the efficiency of task scheduling in the cloud rendering task scheduling, an improved adaptive genetic algorithm based on probability model is proposed in our work. So, the part 2 is the task scheduling of PMGA in cloud rendering. And we will realize the detail of the algorithm from the following sections. The first section is a brief summary of our improvements, and the second section is the encoding way of our algorithm, and the third part is the double fitness function model of our algorithm. And another section is that the probability model and the genetic operations. As you know, our work aims to minimize the time, lower the cost, and keep the load balance of the resources of the rendering tasks. The fitness function generates a fitness value of each chromosome. The value indicates how suitable for solving a task scheduling problem a chromosome is. So it is very important foundation for the algorithm. So in our work, the fitness function is used to evaluate the solution domain, and the fitness function is established for the total execution time and total execution cost of the rendering tasks. And the crossover rate function and the mutation rate function determine the speed of updating and searching for the population. So in our work, the state transferring probability of the Markov model is applied to improve the crossover rate function and the mutation rate function in the genetic algorithm. As for the solution of task scheduling, it needs to establish a mapping relationship between the solution of the problem and the individuals of the algorithm. Taking into account the division of operations on the cloud rendering, our algorithm adopts indirect encoding model to encode the node occupied by each subtask. For example, if users submit 3 tasks in a certain time and they are divided into 10 subtasks, then the resource number of the cloud rendering system is 3. As a result, as the table shows, the chromosome 1, 2, 1, 2, 1, 3, 2, 1, 2, 3 is a feasible scheduling strategy, and we can get the subtask performed on each resource. And then is the fitness function. Our algorithm defines fit time as the fitness function based on the execution time of tasks, and fit cost is the fitness function based on the execution cost of tasks. The formula of them is shown as follows. In this force, Ij is the jth resource of the ith subtask, and the time Ij is the completion time of the I subtask, and the cost Ij is the cost of the ith subtask. Then the fitness function in our algorithm is improved, and it is defined as follows. In the formula, W time and W cost are Wishing coefficients, and W time plus W cost are equals to 1. And actually, the value of W time and W cost can be set according to the user's need. In our experiments, they are both set to 0.5 to balance the proportion of the total time and the total cost. In SGA, the and the SGA means that the standard genetic algorithm. And in the algorithm, the crossover rate PC and the mutation rate PM are both constant values. But in the adaptive genetic algorithm, it has made some improvements based on the fitness value. And the formula of crossover rate function and the mutation rate function are defined as follows. In this formula, Fmax is the maximum fitness value of the population, and Faverage is the average fitness value of the population. F' is the great fitness value of the two individuals which are to have the crossover operation, and F is the fitness value of the mutation individual that are to have mutation operation. And K1, K2, K3, K4 are constant values in 0 and 1. K1 and K3 are equals to 1, and K2 and are equals to K4 equals to 0.5. This is a graph of the crossover rate PC and the mutation rate PM in the adaptive genetic algorithm. As we can see, PC and PM perform a interchange with the increase of the fitness value of the individuals, and they are both equal to 0 when the fitness value is relatively large. The probability calculated by the probability model is applied to the crossover rate function and the mutation rate function in our work. As we can see, the improved crossover rate function and the mutation rate function are defined as the formula shows. And in this formula, F prime, F average, F max are the same as in the adaptive genetic algorithm. And KC1, KC2, KM1, KM2 are constant values in 0, 1, and they are used to control the changing speed of crossover rate and the mutation rate. P, PROC, and P, PRM represents the value of crossover operation probability and the mutation operation probability calculated by the probability model. The graph of PC and PM in PMGA are shown in the figures. As the figures show, PC and PM decrease with the increase of the fitness value, and while F is smaller than F average, PC and PM are still a large value, which close to PCK. So the poor individual have a better ability to evolve, which accelerates the speed of getting the optimal solution. And when the fitness value reaches its maximum value, the value of PC and PM are equal to KC PRC and KM PRM, which is a small value but not a zero value, so that the algorithm can avoid getting into the local optimal solution. According to the process of task scheduling using genetic algorithm on the cloud rendering systems, we get the state transition diagram of the algorithm as is shown in the figure. And the PMGA has the properties of discrete time Markov chain, so it is defined as a discrete time Markov chain D. Each element of Markov chain D is described as follows. The S is a set of finite, non-empty states, and Sint is the initialized state set. P is the migration probability function matrix. It represents the probability of the migration between the modeled system status. And at last, L is a level function, is automatic propositions. And as the Markov chain defines the probability of boundary reachability in the Markov chain is defined as the probability of reaching the state set T from S within K step transition. It is expressed as probable reach ST. And here is the formula of the probable reach. So we can get the calculating method of PPRC and PPRM as the formula shows. And PPRC is the probability from state 0 to state 9, and PPRM is the probability from state 0 to state 11. And in addition, the probability between states in the model are obtained by the running log of the cloud rendering system. The next part is our experiments and analysis about the algorithm we proposed. At first, it's the experimental environment. Our experiments are based on the comprehensive cloud computing service platform, which is made up of 5 clusters, which are consisting of 25 computing nodes, and the tasks scheduled in the experiments are mainly the rendering of pictures and video keyframes. And the table shows the computing node configuration of cloud rendering systems. And the next table shows the main parameters of PMGA and AGA in our experiments. In the first experiment, the total time and the total completion cost using PMGA and AGA are compared, as is shown in the 2 figures. And the 2 figures show the iterative process of getting the optimal total time and the lowest total cost using AGA and PMGA. In these 2 figures, the horizontal axis represents the number of iterations, and in the first figure, the vertical axis represents the task total time. In the second figure, the vertical axis represents the total cost. As we can see from the figures, the convergence speed of AGA is relatively slow at the early evolution process, and is only focused on the total time, resulting in the loss of some potentially good genes and the occurring of local convergence. At last, the task completion time of PMGA is smaller than AGA, and the cost is significantly smaller than AGA. So PMGA converges to the global optimal solution. And the experimental results show that PMGA reduces the total time and lowers cost of scheduling, and it is an effective algorithm for the cloud rendering task scheduling. And this figure shows the comparison of the average fitness value of the new population during the process of the iteration. And in this figure, the horizontal axis represents the number of evolution times, and the vertical axis represents the average fitness value. As we can see, the adaptive genetic algorithm starts to premature convergence at about 16th generation, while PMGA continues to evolve and reaches a larger fitness value, because when the average fitness value is close to the maximum fitness value, the crossover rate and the mutation rate are not a zero value in PMGA. The experimental results show that PMGA has a better ability to do the global searching. And in experiment 2, the number of convergence using PMGA and AGA for task scheduling are compared, as is shown in the figure. The horizontal axis represents the evolution times, and the vertical axis represents the convergence times. We can see from the figure that the convergence number of PMGA is much more than AGA when the number of iterations are the same, are equals. And this experiment results show that PMGA can improve the performance and robustness of the cloud rendering task scheduling. And the last part is a summary of our paper and the future works that we will do. In conclusion, the main goal of our work is to reduce the total execution time and the total execution cost of tasks in cloud rendering system and applying the algorithm to our project. And we proposed a new task scheduling algorithm by applying the probability model and improve the fitness function based on genetic algorithm. And in the future, the Markov characteristics of PMGA will be studied in order to verify the scientifically and relatively of scheduling algorithm using PMGA. And we will focus on the load balancing of dynamic task scheduling on the cloud rendering systems environment, and consider the influence of data distribution, service quality, and other impact factors on the task scheduling results. And that is all. I hope our work has given you some useful ideas, and thank you for your attention and listening.